Welcome to our final chapter for Stat 212. In this chapter, we're going to just be kind of highlighting some important ideas from the class. So this chapter is really, it's not really new content as much as it's just kind of thinking critically about some of the stuff we've already talked about and highlighting a few kind of takeaway ideas from the course. So I'm just going to be kind of doing this more as a short presentation rather than kind of like going through, step-by-step notes, but just kind of highlighting what I think is important that hopefully kind of sticks with you with the course. So the first one is when we're doing statistics, it's important to evaluate your goals. And what we mean by that is whether you're a researcher who is kind of creating a study to answer your question, or just as a normal critical consumer of information who is kind of looking at other people's work. Maybe you have your own kind of question or reason for reading that, and you're kind of evaluating the work that somebody else is doing. It's good to kind of evaluate your goals as well as evaluate the goals of other people who are presenting work that you're reading. And so two ideas in particular under that is just understanding the different types of questions that we might look at with statistics. And this really isn't comprehensive as much as it's just a very simplistic way to kind of divide some questions we've talked about. That there can be questions about understanding one variable that we typically call a univariate, or sometimes it's called a descriptive question, where we're just kind of reporting on, say, income levels. That might be a variable we're interested in, or the rate of COVID-19 infections might be a variable that we're interested in, and we're only interested in reporting it just as a variable on its own and how it's behaving. But that would be different than an associative or a causal question, in which case we're looking at the relationship between multiple variables. We want to understand how they relate to one another. So an associative question is just understanding what that relationship is and how they might move together, whereas a causal question is specifically trying to understand how one thing directly affects another thing. And so an associative question is just kind of a weaker version of a causal question. Causal questions are a lot harder to answer and study because it usually involves an experiment or a lot of very careful data collection. Whereas an associative question is just kind of looking at how two things behave together, but not necessarily understanding what the root cause is, which one might cause the other, or if there's another variable we're not seeing that might actually be the cause of both of these other two, and both of these other two are just kind of the results of something else. So just be very careful about what kind of question you're trying to answer or that other people are trying to answer. And that's going to have a lot to do with the design of the study you're looking at, basically where this data comes from. So we spent about 2 chapters talking about design. So we're kind of, I'm very much simplifying by just saying experiments and observational studies. But just remember that experiments have some kind of intervention. They have some kind of control over that intervention. And these are intended to study causality. Whereas an observational study doesn't have that strength, it doesn't have that ability. Instead, observational studies are just observing what happens. And what we can do is maybe stratify by some possible confounders there. We can maybe understand and kind of control for other things to better understand if two variables might be in a causal relationship. But at the end of the day, it's a lot harder to kind of postulate causality from an observational study on its own. So just kind of keep design in mind when understanding, our ability to identify causality and how that can be compromised a little bit in an observational study. That it requires a lot more kind of work, a lot more controlling of other confounding variables to have a better theory about what the causal relationship might be. Secondly is assessing the validity of the designs that we see. So that was kind of a background of like understanding our goals through the question design at hand. And then secondly, given that question and given that design, how valid is that study? How well was it done? And how well does that particular design kind of answer that question? And so we can kind of think of this through validity in 2 ways. One is what we call internal validity, and one is what we call external validity. Internal validity is about the relationship itself within the experimental setting. So if we're looking at an experiment, it's within the experimental setting. If we're looking at observational study, it would be within the units that we have observed. And how well did the study effectively identify a link between these two variables, whether it be a causal link or at least maybe a correlational link. Like what are the other kind of confounders that could affect this relationship, in particular with causality? Can we be confident that there is a causal relationship, or is it possible that there's other confounders that weren't controlled well with this particular study? That gets into things like, were the groups equivalent to each other? If I'm comparing the effect of one group to another group, was the group composition balanced appropriate? Do I have similar people in each group? It might be, were the timing effects the same, or does one group maybe have a different timing that could affect the results? Was the instrumentation appropriate? All those kinds of questions matter with internal validity. External validity gets at, given this particular study, given this data that I have, how well does the results that I observed here generalize to a kind of broader setting? How well do they generalize to other people in other times and other places? And so that gets at, how useful are these results? Maybe I did replicate, or maybe I did have this particular result here, but could I replicate this in different settings with different people? So if I only have, say, people between the ages of 18 and 25 in my study, well, does this result generalize to people outside of that age bracket? Well, that would be kind of a big question mark. So thinking about both the internal validity, is the study itself valid in finding a causal link, as well as external validity, can I generalize what I found to other people, settings, and times? Both of those are important to consider when both designing a study and evaluating somebody else's work. If you're doing your own study, before really digging into analysis, I would always encourage folks to look at their data. Like, visualize your data, look at the raw data, honestly, look at the summary stats, just understand what's going on and keep the context close as you're doing that. Because even with, say, like the survey that we do in this class, I would need to look at the data, number one, just to make sure people understand what the questions are. Like, I can find a variable and see several responses that don't make a lot of sense, and I'd have to go back to the survey and see, oh, this question probably got misinterpreted by a number of people. Like, I think there was one semester where I asked people what their height was in inches, but I had a lot of people, not a lot, but several people who said like 5.5 or 6.1, and I think what they were doing was listing their height in feet. And so you just want to be kind of careful looking at your data to understand, is the data good? Was it understood appropriately by the people that were asked? Do I have okay measurements? But it also just gets into things like anomalous readings, that maybe it wasn't so much a mistake as much as it's kind of something unusual that happened. Or just understand kind of the story of what's going on. So looking at your data is just a really important step to understand what happened before you kind of go into analysis and deciding, what exactly do I want to test here? Do I need to remove any data that might be a problem, that might be just incorrect, that might be anomalous, that might kind of signal that maybe there's another grouping or another kind of cluster, that maybe I want to separate these clusters before I do any further analysis to kind of analyze within different clusters instead. Those are the kinds of things I would need to think about contextually before I just jump into a hypothesis test or a linear model or something like that. I brought this picture here as well about the elephant. So I've heard different variations of this, but this idea of kind of, an elephant, if you look at it holistically, is an animal that makes sense. But if you look at an elephant close up at different places, you see kind of different stories. You see different things. You see, the trunk is very different than the tail, which is very different than the body or the ear or the leg, right? Those are all different aspects that if I zoom in too close to one part, I don't have the whole picture of what's going on. And so that's why it's probably important when you kind of when you do your data analysis, you want to step back and look at your data. You want to look at, where does it come from? You want to look at, what kinds of measurements do I see, both at the beginning and at the end. Maybe the story changes based on when people kind of entered their data or who was collecting that data, as well as just kind of understanding, how different variables can relate to one another, and how like maybe the sequencing of how the data was collected, maybe with people taking a survey, was there an ordering to the questions that might matter too? So all those things are very relevant and are very contextual that we can't really teach very well in a statistics class because we're so focused on the methods, but it is important to kind of take back to your discipline when you're collecting data and trying to answer research questions. One thing that is very specific to what we did is just understanding that we're almost always just collecting samples of larger populations, or we're collecting samples, that could be replicated infinitely many times to try to understand a process or a system. And whenever we collect a sample, we have to recognize that our sample statistics are almost always going to have at least some error in estimating what the true parameter is going to be. And so one way that we commonly quantify that error is with a measure called the standard error. And every statistic has a standard error that you could calculate that tells you, on average, how far off from the parameter should we expect the statistic to be. Sometimes our statistic's closer, sometimes our statistic is farther, but this is kind of an average amount of error based on our sample size and based on the variability observed with the sample that we have with the measurements. And so when you report a statistic, it's common to also report either a standard error or a confidence interval for that statistics, like a 95% confidence interval that kind of measures, we're 95% confident the true parameter should be in this range around the statistic. This is how far we kind of, could reasonably think the statistic could kind of vary from that parameter. So yeah, our statistics almost always have error, and we need to quantify what that error is. Our statistical conclusions should be multifaceted. This is kind of hard to get across in an intro stat class because we haven't covered a lot of methods. There's kind of a lot of, we get so wrapped up in p-values because this is a really common measure to use, and it's usually a very kind of fundamental measure to use. But there's a lot of other ways to kind of understand relationships between variables. So keeping in mind what a p-value is and what it's not is important. That number one, a p-value is helping us provide indication of confidence that there is any departure from the null hypothesis. It doesn't tell us how much that departure is. It only tells us whether or not, like probabilistically, this is a result that we would see if the null were true. So that when it's low, we have a low p-value, that means we have confidence that maybe the null hypothesis isn't true. And that's different than an effect size, which is a scaled measure of the magnitude of that departure from the null. So the effect size is a lot more helpful for understanding how big that departure might reasonably be. And context is important for determining, which of those things is kind of important to us, whether it be both of them or whether it may be one of them more than the other is more important for answering a question. But just realizing that p-values and effect sizes are kind of telling us two slightly different things that can help us answer slightly different questions. And then lastly, just kind of keeping in mind that our analysis isn't always just defined to like one t-test, but often it's going to be a little bit more holistic where we're kind of looking at our visualizations. We're looking at our statistical test results or our model result, and we're trying to write a cohesive story that weighs all of this information, that is trying to share what we did find from our data and maybe some things that we didn't find from our data, things that we can't quite claim or things that we don't quite know based on this sample of data. So, even if you fail to reject your null hypothesis, it's not that we don't conclude the null is true. We don't know if there is indeed no difference at all. Rather, we're just saying that we didn't have enough evidence. There wasn't enough reason in our sample result to conclude otherwise, that therefore it's possible the null could be true there. So always kind of think of your statistical conclusions as multifaceted, where all this information, your visuals, your test results, possibly a model or something like that, are all kind of contributing to your story there. And lastly, this one's important to me because this is something that I have personally learned as a researcher, that data is more than numbers, and that it's really, I see this a lot, especially with kind of early researchers, is like kind of overemphasizing the numeric results as somehow being more objective than, say, interviews or anything like that. And so the truth is quantitative research is a lot easier for collecting a lot of information but usually getting a lot of kind of brief snippets of information. So quantitative research, e.g. statistics, is best for identifying and measuring patterns, effects, and anomalies that can't be explained by random chance, and kind of collecting that from a large swath, or I should say from a sample of the population that helps us kind of make a claim about what could be true about the population. Qualitative research is another kind of arm of research that's usually best for explaining why such patterns, effects, and anomalies exist, because it gets at kind of a richer type of data. Oftentimes you see observations, maybe an ethnographer is kind of studying a culture or a community. You might see qualitative research through the use of interviews, through community observations. Um, these are also really important ways to collect data, and they're no less valid as much as they're just different in what they help us see. They help us understand why things happen, and they help researchers kind of postulate theory as well. So data comes from both numbers and words. So when you're kind of tackling research questions, maybe beyond this class, you're going to do some research. Just keep in mind that all of this is helpful, and don't just over objectify the numbers as somehow being the holy grail of data and evidence, but rather all of this information can kind of help us understand holistically what could be going on. And then lastly, I'll just kind of give a plug to Keep Learning. We've kind of scratched the surface as an accelerated introductory statistics class with a focus on kind of biostatistics questions. But you can always learn more, whether it be through actual coursework. So for example, we have a statistical programming class. If you really enjoyed learning R and you want to take more programming, Stat 385 is a class that you can jump right into. You could take a calculus-based statistics introduction with Stat 400 if you've taken through Calculus 2. That's also kind of a gateway to taking more classes as well. You could take a whole linear modeling class. Currently, that would be Stat 420 that you could take after you've taken Stat 400. And that's really helpful if you, again, want to learn more R and just want to get more experience with creating models for purposes of prediction. We have a special topics course. I don't know when it will be offered, but on epidemiology, probably maybe once a year this is going to be offered, so just kind of be on the lookout for that. I believe, I don't know what the prerequisites are, but maybe that might be of interest to you. And then besides coursework, just searching for help online, asking a more knowledgeable other. I do these things all the time. If you're ever actually doing analysis and you just have questions, there's a lot to learn. I have a lot to learn too, honestly. So I hope that you kind of take that to heart if you're ever doing research and kind of look for information as you need to.